Hello everyone, my name is Mariana, I'm Portuguese, and I'm a student of the doctoral program in biorefineries. My PhD is integrated into the Impactus project, which is related with innovative products and technologies from eucalyptus. Today, I'm going to show you the main results of the valorization of eucalyptus globus bark through enzymatic hydrolysis for the production of cellulosic sugars. So, I'm going to start with a brief introduction regarding the main steps involved in the conversion of bark into cellulosic sugars. Also, I'm going to present you some of the advantages of its integration in the pulp and paper sector. Finally, I'm going to present you the main results and the conclusions. The pulp and paper industry is the major consumer of woody biomass, but why Eucalyptus globus? As you know, Eucalyptus globus is the main wood source of pulp and paper industries of Australia, South America, but also in Portugal. Its high productivity and high cellulose content are the main advantages of eucalyptus. The debarking is a key operation of the wood handling and generates a huge amount of bark. The presence of bark in a significant amount compromises the yield but also the quality of the pulp. Nowadays, most of the bark is burned for energy and steam generation. However, bark has the potential to be converted into more sustainable and cost-effective applications. A potential route is the production of cellulosic sugars, which is recognized as a platform for biochemicals and biofuels. So, the conversion of eucalyptus globus bark into cellulosic sugars involves two main stages, the pretreatment and the hydrolysis steps. The main objective of the pretreatment is to improve the exposure of the carbohydrates to the hydrolysis agents. In our case, we used the kraft pulping process as a pretreatment for the bark, since it is a delignification technology widely used in pulping industries. The main objective of the enzymatic hydrolysis is to convert the polysaccharides into simple sugars. So, the integration of the production of cellulosic sugars from bark into the pulp and paper industry allows us to add value to the raw material not suitable for the pulp production. Also, it contributes to a sustainable waste management system and for the circular economy model, boosting the market opportunities of this sector. In this context, this work aimed to evaluate the effect of the residual lignin content of the raw material, the type of agitation, and the different mechanical impellers on the production of cellulosic sugars from eucalyptus globus bark kraft pulp. Also, we evaluate the impact of increasing solids loading content through a fed batch approach at 3-liter scale. Regarding the chemical characterization of the raw material, we found that kraft pulps are mainly composed by cellulose and hemicelluloses, accounting for a carbohydrates fraction higher than 75% depending on pulping conditions. Also, we found that kraft pulps has a residual lignin content lower than 7%, which means that kraft pulping process is an efficient pretreatment for the bark. So, we started by comparing the orbital and mechanical agitation systems. However, we didn't find significant differences regarding the production of cellulosic sugars, probably due to the small scale. In any case, it was possible to observe that the mixture started to liquefy earlier when we used a mechanical agitation system. Also, it is important to note that the orbital agitation system is not suitable for operation at high solids loading content, neither for the scale-up process. After, we assessed different mechanical impellers and we concluded that at this scale, all the agitation systems showed a good and similar performance. It was achieved an hydrolysis yield of about 90% and a concentration of cellulosic sugars of about 45 grams per liter. The highest cellulosic sugars concentration of about 92 grams per liter was achieved using the 3 radial glass plates and a raw material with a lower residual lignin content. Regarding the delignification degree, it was clear that the higher the residual lignin content, the lower the production of cellulosic sugars and consequently the lower the hydrolysis yield. It was also found that combining the high lignin content with a high solids loading increased the time required to liquefy the mixture. According to these results, we selected some operational conditions for the scale-up process. First, we used a kraft pulp with a kappa index of 15, which is a trade-off between the kraft pulping process severity and the residual lignin content of the raw material. Also, a new blade was used to improve the homogenization of the reaction mixture. Finally, we was able to increase the solids loading content to 20% by using a fed batch approach. It was achieved the highest cellulosic sugars concentration of about 160 grams per liter. However, a lower hydrolysis yield was attained, which can be related with some technical issues. So, we concluded that the residual lignin content has a significant impact on the production of cellulosic sugars. Regarding the assays performed using the small bench scale reactors, they showed a great hydrolysis yield of about 90%, and the concentration of cellulosic sugars ranged from 44 to 92 grams per liter. The highest cellulosic sugars concentration of about 160 grams per liter was achieved using the fed batch approach at 3-liter scale. Although we concluded that this process should be optimized to simultaneously maximize the production of cellulosic sugars and the hydrolysis yield, this work proved that kraft pulp from Eucalyptus globulus bark has a high potential to be converted into cellulosic sugars, contributing to the circular economy model. Before I concluded my presentation, I would like to thank the organization of Tecnicelpa for the opportunity, thank Impactus Project and partners for the financial support and my PhD grant, and finally, thanks to my supervisors and colleagues for all the support. Also, I would like to thank you all for your attention. Thank you.
Hello, my name is Paulina Mocchiutti and I'm going to talk about the effect of ethanol on the mechanical properties of film obtained from colloidal suspension of xylane and chitosan. This work has been made in the National University of Litoral, Santa Fe, Argentina. The hemicellulose are one of the most abundant polysaccharides present in the lignocellulosic biomass. According to the procedure used for extracting the hemicellulose, different molecular weight can be obtained. The alkaline extraction process is commonly used for obtaining high molecular weight hemicellulose. This kind of hemicellulose can potentially be used for the production of bio-based film. They are usually combined with plasticizer with nanofibrillate cellulose and high amount of plasticizer, or they are combined with another polymer or polyelectrolyte. These films show excellent oxygen barrier properties. They are not toxic and they are biodegradable. Nevertheless, due to their hydrophilic nature, they show poor water vapor barrier properties and they are sensitive to water. Besides, they show relatively low mechanical properties. Xylane is the main hemicellulose present in hardwood. It's a linear and weak polyelectrolyte. It presents one glucuronic acid each 10 xylose unit. Due to this glucuronic acid, xylane can be considered as an anionic polyelectrolyte. In a neutral or alkaline medium, this acid group is ionized. Besides, the acetyl groups are removed. On the other hand, chitosan is a natural polymer derived from the deacetylation of chitin. It's also a linear and weak polyelectrolyte that in acidic medium is ionized. The amine group is cationized and due to that it's considered as a cationic polyelectrolyte. Then, polyelectrolyte complex suspension can be formed by combining a cationic polyelectrolyte such as chitosan with an anionic polyelectrolyte such as silane. The use of polyelectrolyte complex has been increasing in the last year for industrial application. On the other hand, ethanol is commonly used for precipitating the hemicellulose dissolved in the alkaline extraction process. Besides, ethanol is used for purifying the hemicellulose. In the photograph, we can see poplar wood silane precipitated using different ethanol water ratios. The properties of the water ethanol solvent essentially differs from that of both pure solvent. Due to that, the residual solvent present in the precipitated hemicellulose could modify the characteristic of the colloidal suspension and could improve the mechanical properties of the film. If this is the case, silane can be used directly from the alcoholic suspension without the need of the drying step. Then, the objective of this work was to evaluate the effect of the presence of ethanol on the characteristic of silane chitosan polyelectrolyte colloidal suspension and on the mechanical properties of film. First of all, silane was alkaline extract from poplar wood of 12 years old. Wood flakes were prepared and they were treated with sodium hydroxide in a 50-liter reactor in our pilot plant. Then the silane dissolved was precipitated, used ethanol, and highly purified and characterized. On the other hand, chitosan was supplied by Sigma Aldrich. For the preparation of the polyelectrolyte complex suspension, the drop-wise addition method was used. Silane containing different amount of ethanol was added on chitosan solution. This complex suspension was prepared at pH 5. Then for the preparation of the film, the casting evaporation technique was used. Then the film were evaluated before washing the film and after washing and re-drying the film. Different methods were used for characterizing the simple polyelectrolyte, the colloidal suspension, and the film. Results show that using potentiometric titration, we can determine the degree of ionization of silane and chitosan. It was found that with increasing the amount of ethanol, the degrees of ionization of both polyelectrolytes were slightly decreased. Then it is expected that when polyelectrolyte complexes are formed, the ionic interaction between them will be reduced. Using dynamic light scattering, the average particle size of the complex were determined. The figures show the average particle size as the function of ethanol concentration. The figures show that with increasing the amount of ethanol, the average particle size of the polyelectrolyte complex were decreased. This could be due to the reduction of the ionic charge in the system, as was explained before, which decreased the swelling of the particle. Besides, the ethanol reduced the water solvating envelope around the polymer chain, which promotes hydrogen bond between polysaccharides. Using dynamic light scattering, the zeta potential values were also determined. The figures show that all the colloidal suspension were cationic and stable suspension. Besides, the figures show that with increasing the amount of ethanol, the zeta potential values were increased. This is expected consider that the specific sulfur charge of the particle is increased due to the reduction of the particle size. Here we can see films obtaining using different ethanol concentration. The photograph shows that up to 12% of ethanol homogeneous and transparent film and also glossy film were obtained. Nevertheless, when 16% of ethanol was used, opaque and less homogeneous film were obtained. These films were used for determining the crystallinity of them. To do that, X-ray diffractor analysis was used. The figure showed the diffractogram of silane chitosan film without the presence of ethanol. The diffractogram is characteristic of material that present crystalline and amorphous region. The diffractogram presents a broad peak around 19-20 grades. Then, with increasing the amount of ethanol, the intensity of the major peak is decreased, probably due to a better interaction between silane and chitosan that produce a more amorphous material. Nevertheless, when 16% of ethanol, the peak significantly increased, probably due to an increment of the crystallized insoluble polymeric portion of the polysaccharide. Interaction between polymer segments could produce aggregation, and due to that, we see opaque film. On the other hand, we determine the dry state mechanical properties of film before the washing step. Here we can see the stress-strain cure of film without the presence of ethanol. These films show acceptable mechanical properties. Nevertheless, with increasing the amount of ethanol up to 12%, the stress significantly increased up to 35 megapascal, and the strain showed a tendency to increase up to 30%. Nevertheless, when 16% of ethanol was used, the stress significantly decreased. Here we can see the properties of the film obtained after washing and redrying the film. Here we can see that the control film without the presence of ethanol showed significantly higher stress at break. This could be due to a rearrangement of the polymeric change when films were redried, with the subsequent creation of new bonds that generate increased strength. Again, with increasing the amount of ethanol, this property increased. When we use 12% of ethanol, the stress obtained was 75 megapascal. These stress values are higher than the reported by others. The strain at break was 6%. Besides of that, the film were easy to handle. Again, when 16% of ethanol was used, the stress was decreased. Finally, the water vapor permeability, swelling, and solubility were determined. It was found that the water vapor permeability did not change. Nevertheless, the swelling significantly decreased, and the solubility obtained were low. As conclusion, we can say that the presence of up to 12% of ethanol in the silane chitosan colloidal suspension led to films of remarkably high mechanical properties. The ethanol led to a greater association between the polymers of silane and chitosan. This greater association in the PET colloidal suspensions reduces the size of the complex and increases the stability of the suspension. And in the film, allows the formation of amorphous, transparent, and easy to handle film with stress value as high as 74 megapascal and stress value of 6%. Besides this greater association, reduced swelling by 12%. On the other hand, higher amount of alcohol in the medium led to more opaque film mainly due to the formation of higher crystalline region. Results show that for preparing film, it is not necessary to remove the residual ethanol used for silane precipitation and purification. Anyway, it should be necessary to limit the concentration to lower than 12% ethanol in the silane phytosan colloidal suspension. Thank you for your attention. Thank you, the organizing committee, and thank you for this institution.
Hello everyone, I am here to present my work on black liquor fractionation by polymeric membranes. To begin with the introduction and motivation of this work, I will talk about the Kraft pulp mill operations, membrane filtration process and development of mixed matrix membranes. Further, in the experimental part, the process of zinc oxide based mixed matrix membrane preparation followed by black liquor characterization and filtration using dead end configuration will be discussed. Later on in the results, I will discuss the membrane's characteristics and their performance in terms of black liquor filtration. Finally, I will sum up this presentation with the conclusions. In Kraft pulp mill operation, lignocellulosic raw material is cooked with cooking chemicals in extreme temperature and pH conditions to produce cellulosic pulp. The main aim of pulping process is to remove the lignin, but almost 50% of original raw material get dissolved in the pulping liquor. The spent pulping liquor along with the washing water make up the weak black liquor and generally considered as waste stream. In the conventional pulping industry, this black liquor is concentrated with evaporators and burned in the recovery boiler where the inorganic cooking chemicals are regenerated and organic components are utilized to produce process steam and energy. The development of biorefineries concept has triggered the global interest towards the identification of high potential wastes generating from the biomaterial based industries. Black liquor fits as a perfect example for this category as it is economically available and not so well utilized. The various studies has proved that the main organic component of black liquor, namely lignin and hemicelluloses, can be used for the production of high-value products. For instance, lignin can be used for the production of phenol, formaldehyde resins, absorbents, carbon fiber, etc. Likewise, hemicellulose can be used for the formation of hydrogels, additives and biofuels. However, for the development of these lignin and hemicellulose based products, first requirement is to separate these components from black liquor. For the fractionation of black liquor, the filtration process using both ceramic and polymeric membranes have shown promising results. Membranes are semi-permeable materials which separate different components mainly based on their size, charge and solubility difference. These have wide range of application due to various advantages like simple and flexible in operation and low chemical and energy consumption. However, besides these advantages, the low thermal and chemical stability of polymeric membranes, low separation efficiency of ceramic membranes, and membranes fouling limits their commercial state utilization for the black liquor fractionation. Among all these limitations, the fouling has been identified as most critical bottleneck for all types of membranes. Due to the fouling phenomena, membranes permeate flux and their separation performance reduces along with the filtration process. To overcome these problems, new development in the membrane technology is the mixed matrix membrane. The mixed matrix membranes are nanocomposite membranes having properties of both polymeric and ceramic membranes. Based on the application and the nanoparticles incorporated, these membranes can have high separation and performance, more surface hydrophilicity, higher thermal and chemical stability. Nanoparticles can be incorporated either in the polymeric membrane matrix during the preparation process or on their surface by surface treatment of simple polymeric membranes. In this work, we studied the application of commercial ultrafiltration membranes made of polyether sulfone and preparation and application of zinc oxide based polysulfone membranes for the fractionation of black liquor. Moving to the experimental part, For the preparation of mixed metric membranes, polysulfone as main polymer, zinc oxide nanoparticles as filler, and methyl pyrrolidone as solvent, and polyethylene glycol 400 as pore forming agent were used. Three different types of membrane having 0, 0.4 and 0.8% zinc oxide concentration were prepared. For the application of the prepared and commercial membranes, the industrial craft black lacquer was used. The primary characteristics of black lacquer are shown in the second table. The total solid content of black lacquer was approximately 17%, and lignin and hemicellulose concentrations were measured as 85 gram per liter and 13 gram per liter. Moving further to the process of zinc oxide based mixed metric membrane preparation. These membranes were prepared by non-solvent induced phase inversion process. First, a homogeneous suspension of zinc oxide in NMP solvent was prepared by stirring and ultrasonic treatment. Then polysulfone and polyethylene glycol were mixed to this suspension, and mixing was continued overnight at 70 degrees temperature to obtain a homogeneous casting solution. The prepared solution was spread over glass plate using casting knife. The prepared membranes were solidified by immersing these into distilled water used as a non-solvent. The second scheme represents the configuration of stirred cell, which was used for the filtration of water and black liquor. All the water filtration tests were performed at room temperature, while for black liquor filtration 60 degree temperature was maintained to minimize the effect of viscosity. Further, I will discuss about the characterization of the commercial and prepared polymeric membranes. Talking about the membrane characterization, in figure 1 we can see the effect of transmembrane pressure and time on the water flux for the commercial membranes. The data from this plot was used for the determination of pure water flux using equation 1, which is reported hereby in this table. Further, the flux values were plotted against the transmembrane pressure to calculate the average permeability of these membranes, which is shown in figure 2. Here we can see that the hydraulic permeability of commercial membranes was calculated as 39.29 unit. Similarly, the prepared polysulfone membranes were characterized. As we prepared three types of polysulfone membranes using three different concentration of zinc oxide nanoparticles. The figure 3 shows the permeability of membranes prepared without zinc oxide and 0.4% zinc oxide concentration. By comparing the permeability of these two membranes, it can be observed that the addition of 0.4% zinc oxide, the membrane's permeability was increased approximately 2.5 times compared to simple polysulfone membranes. Further increasing the zinc oxide up to 0.8% resulted into 3.5 times higher permeability than the simple polysulfone membranes. This increase in permeability can be explained by the fact that the addition of zinc oxide in membrane solution can influence the kinetics of phase separation during its preparation. The zinc oxide nanoparticles can accelerate the exchange of solvent and non-solvent, facilitating the formation of large pores and enhanced porosity. Further, to see the effect of zinc oxide addition on hydrophilicity, the water contact angle of prepared membrane surface was measured. Here we can see that initially with the zinc oxide addition up to 0.4%, hydrophilicity increased, and then it decreased for 0.8% zinc oxide membrane. This can be explained by the superior dispersion of nanoparticles in membrane matrix up to 0.4% concentration, resulting into smoother surface which can provide more space for the spread of water droplets. However, with the further addition of zinc oxides, the nanoparticles start agglomerating in the solution, which increases the membrane surface roughness and resulting into higher water contact angle. Comparing the permeability of prepared membranes and commercial membranes, it is clear that permeability of all the prepared membranes was significantly lower compared to commercial membrane. Hence, only M3 which was having 0.8% zinc oxide and presented the best permeability among the prepared mixed metric membranes were employed for the black lacquer filtration along with the commercial membranes. The separation performance of M3 and commercial membranes were analyzed by characterization of black liquor permeate collected from the filtration at different pressures. As the permeate flux from M3 was very low, the filtration was performed only at 2 and 4 bar pressure. The collected permeate samples were analyzed for lignin and hemicellulose concentration. Further, using equation 3, lignin and hemicellulose rejection was calculated for both membranes. As we can see that both membranes showed the opposite trend of rejection with the increasing pressure. As it increased with increasing pressure for commercial membranes, which is a usual behavior. However, it decreased for the prepared zinc oxide based membranes, and the unusual behavior for prepared zinc oxide membranes can be due to high fouling of these membranes with increased pressure. To analyze the fouling, the black liquor permeate flux behavior was analyzed with the filtration time at 4 bar pressure for both M3 and commercial membrane. In figure 5A and B, we can see that both membranes presented low initial black liquor flux due to the complexity of black liquor, which further went on reducing along with the filtration process due to fouling phenomena in both the membranes. Now, summarizing the performance of both membranes at 2 bar and 4 bar pressure, it can be observed that commercial membranes presented promising result for black liquor filtration in terms of flux and lower flux reduction compared to prepared zinc oxide membranes. However, at 4 bar pressure, for the zinc oxide membranes, the lignin concentration and permeate was towards higher side compared to commercial membranes, offering them higher selectivity at high pressure. Finally, by analyzing all the results, it can be concluded that by incorporation of zinc oxide resulted into increased permeability and hydrophilicity for the prepared mixed metric membranes. For the black liquor filtration, commercial membranes presented highest flux and rejection. However, the filtration properties and fouling resistance of zinc oxide based mixed metric membranes can be improved further by optimizing the polymer and nanoparticle concentration. In the end, I would like to acknowledge the project Impactus for funding this research. Further, I would like to thank Professor Licínio Ferreira, Professor Helena Gil, and Dr. Patricia Als for their kind supervision. Thank you all for your kind attention.
Hello, good afternoon to all. For me, it's a great pleasure. Hello, a great pleasure to introduce you these section's speakers and their topics for discussion. But I will present myself. My name is Paula Pinto, and I work at the Forest and Paper Research Institute. Now in live we have Licínio Ferreira from University de Coimbra, Mariana Amândio from University of Coimbra and University of Aveiro, both, and Paulina Mocchiutti from Universidade Nacional del Litoral, Santa Fé. So thank you all for your excellent presentations. Just a brief note, Manorma was the presenter of the black liquor fractionation, my membrane processes, but she is not available, and therefore we have Licínio Ferreira, her supervisor, for the discussion. Are you hearing me? Yes? Okay.
Yes.
Yes.
So there are several questions already in pipeline. But in meanwhile, I would like to start with a general comment. For me, it's very interesting to read your work and to see your presentations, and to note that each of these topics on this section is related with the biorefinery model that eventually could be seen as an integrated perspective. What I mean is that your work is complementary. Starting with Mariana Amândio, she requires kraft pulping to produce the raw materials for sugars. And from kraft pulping, we get the black liquor for separation or fractionation by the membrane processes, producing then a silane-rich stream. that interesting could be taken by Paulina for films, bio-based films. And exactly, Paulina, starting by you, I would like to make these questions. This question: how do you see other kind of silence to be used to your process, to your bio-based films? What's the specification of the silence for this proposal?
Yes, we have made trials and we publish films using silence from birchwood, and in our group they are also using bagasse silence. In this case, we found higher properties using poplar silence. This silence was extracted in our pilot plant. This silence was characterized, we determined the purity using the phenol sulfuric acid method and the Scott method for determining the amount of acid groups. And then we characterized the films obtained as we showed.
Okay, but is molecular weight an important parameter? For example, how do you see the xylans in black liquor? Do you think that could be a source for your particles and films?
Sorry, the last part?
About the silence. Let's see if we can get a process to fractionate black liquor like this one in the separation by membranes, and if you get hemicellulose rich stream, so composed by silence, how do you see the application of this silence in your process? Is the molecular weight very important?
Yes. We think that the molecular weight is very important. Due to that, we use an alkaline extraction process to isolate the silane.
Okay, thank you, Paulina. So I will move to questions from the audience. Mariana, could you tell us about the type of enzyme and the enzyme loading, as well as strategy used for adding enzymes in your fed batch hydrolysis?
Yes, regarding the enzyme consortium, I cannot provide you some details because we have a confidentiality agreement. But regarding the enzymatic loading, I used 25 filter paper unit per gram of carbohydrates. Regarding the last question about the fed batch strategy, I added all the enzyme at the beginning of the process.
Okay, Mariana. And have you tested those cellulosic sugars as fermentation substrates?
Yes, I already tested the fed batch hydrolysate for the production of bioethanol. Actually, I have a good performance and I can achieve a concentration of ethanol higher than 40 grams per liter, which correspond to a yield higher than 70%.
Okay, thank you, Mariana. And
Thank you.
now for Licínio. What could be the constraints in your perspective for the implementation of a membrane process at industrial scale to recover the hemicellulose from the black liquor? Can you give some insights about this?
Okay. The first part of this project is to perform several experiments at the laboratory scale in order to optimize relevant operating conditions. Okay. The first set of experiment were carried out in dead hand mode using a cell, and next the other set of experiment will be performed in cross-flow mode. This is the normal mode in membrane units operating at industrial scale. Okay. When you use membrane process for in order to get a target separation, it's very easy to scale up in order based with laboratory data. It's very easy to scale up in order to design a unit operating at large scale. Okay. There is a limitation. Is the membrane falling? Is a very strong limitation, and during the presentation we present some results with using modified membranes, mixed matrix membranes. Okay, the idea is to incorporate zinc oxide nanoparticles in order to improve or to mitigate the membrane falling. And on the other hand, when you introduce zinc oxide nanoparticles, it's possible also to increase the hydrophilicity of membrane surface. And this point is very important because it can affect the selectivity. When the objective is to separate hemicellulose and lignin from black liquor. Okay. Of course, you can ask, okay, you prepare this kind of membranes. The membranes are flat sheet membranes, okay? At industrial scale, normally the configuration of the flat sheet membranes, normally in big scale or in large scale, the units are equipped with or tubular configuration or hollow fibers configuration. Okay, but it's possible with the results obtained from the laboratory regarding these kind of membranes, it's possible to scale up and to get, for example, another configurations. Okay, the main point is the membrane composition. I don't know if I clarify.
Yes, thank you very much. So we move to another question for Paulina. Paulina, did you carry out biodegradability tests on your films?
Not
what
yet.
Can you say about it?
Yes, not yet on this film, but with other film using bagasse and kaitosan, we have made this trial. And the biodegradable is, they are biodegradable, but we didn't do on this kind of film, this film.
Okay, thank you, Paulina. Mariana, you have studied bark pulp as raw material for sugar production. Usually, conventional unbleached pulp is a reference for comparison. How does the values obtained for pulp from bark compare with those from wood pulp? Better, worse? Do you have some figures to share?
Yes, the performance is a little worse, but it's not so big difference. I have a difference about 10% of the yield or lower compared to the unbleached craft pulp. So I think it's a good result.
Yes, for bark, for sure.
Yes.
Paulina, can you share some purification methods you used for separated silane, isolated silane?
Yes. First, the silane was precipitated using a 1:1 water ethanol ratio. Then the silane precipitated was centrifuged, and then it was again dissolved in hot water, filtered, and this silane, the filtrate was again mixed with ethanol up to 1:1 water ratio. This you can do that several times up to obtain the solid. Then, the ethanol could be evaporated in an oven or at low using vacuum.
Okay, thank you, Paulina. Mariana, for a better understanding by our audience, could you please elaborate a little bit about the importance of fed batch operation in enzymatic hydrolysis? In fact, you have obtained a very good final concentrations in sugars, but not yield yet, right?
Yes.
But can you elaborate about that? Maybe for fermentation purpose, it could be interesting.
Yes, regarding fed batch strategy, I can achieve a high sugar concentration because we started with 11% of solids loading, and after each 2 hours, we had 3 fresh solids until achieving 20 solids loading in the final. However, the yield was lower than we expected, maybe due to some problems related with mass and heat transfer. And also, I think we should tested some more extended saccharification periods. I think if we prolong the enzymatic hydrolysis, we can achieve higher yield. However, we should establish a compromise between the yield of enzymatic hydrolysis and the operation costs. So we perform it only during 24 hours. But I think if we perform the enzymatic hydrolysis for 48 hours or more, we can achieve higher yield, but we have to establish a trade-off between the yield and the costs.
And The following question is related with that. Let's imagine that how you choose to not to get so higher yield, so you will get some solids, final solids,
Yes.
not hydrolyzed. So do you consider to evaluate these final solids, residual solids after hydrolysis, and to valorize, to make some, to evaluate and to study some applications?
Yes, it could be a possibility. These solids maybe are rich in lignin, so maybe we can find some applications for its solids.
Okay, thank you, Mariana. Just another question for you. What about the addition of substrate to reach your 160 grams per liter?
I already answered this question. I
Yeah,
think it's about
yes,
fat.
yes. Fed batch is with fed batch. You reach this with the fed batch, right? And for Licínio, about membrane, do you consider to modify another type of membrane, or in other words, you choose polysulfone membrane to start? Do you consider to use another one with better performance eventually?
Another polymer?
Another polymer, yes.
We choose the polysulfone. Why? Because the polysulfone is a very resistant polymer. Okay, when you work in aggressive conditions, okay, polysulfone is a very resistant polymer. Okay. For example, if instead of polysulfone, if I use for example, cellulose acetate, okay, is a polymer, is not resistant at alkaline conditions, okay? For example, you know the black liquor is a very complex mixture, okay? With the pH is 12 or 13, okay? It's not possible to use cellulose acetate and in this condition. Okay? But polysulfone is a very suitable polymer for this kind of thing.
Yes, and about the falling, that is a problem related with the membrane processing, and of course with black liquor, which is a very complex mixture, even first. Yes. Do you think that a previous black liquor treatment could be interesting to reduce the falling and eventually to improve the performance? I was thinking about, for example, microfiltration before ultrafiltration, or some kind of other treatment.
Of course, is a approach can be used. Okay, is like a pre-treatment. Okay, before to use the ultrafiltration. Okay, but there are several approaches, and in order to mitigate the membrane falling, okay, and this kind of approach can be useful to pre-treat the black liquor before to process the black liquor in ultrafiltration membranes.
Okay, thank you. For Paulina, what solids active xylene ketosane concentration have you been able to achieve?
Ketosane solution was 2.5 gram per liter, and xylene 4 gram per liter. This solution were mixed to obtain the complex.
Okay, Paulina. And about the film thickness that you get in the final, I think you have this information in presentation. The film thickness, no, or in the abstract, in the extended abstract, yeah.
60 micron, 60.
Okay.
Micron.
And Paulina, a general question. What is the main application for these films? In your opinion, do you think that this could be applied on paper for special purposes?
Yes, it's probably, but the problem of this film is the low water vapor barrier properties. And perhaps if we can improve that, for example, using an hydrophobic molecules or other or higher cross-link, we can improve that properties. This film, other application could be this film, because they have a high oxygen barrier properties. It could put between two films of petroleum-based film in the middle of these two films. For example, a low-density polyethylene that has a low oxygen barrier properties and good water vapor barrier properties.
Okay. Let's go to another question. Mariana, are you the 160 grams per liter, again, is a sum of exoses and pentoses, right? Or
Yes,
only
yes.
glucose? Is the sum?
Yes, is the sum of glucose and xylose.
Okay. Thank you very much. About the eventually a scale up, Mariana, of your work and your system. You have made a first step to scale up the enzymatic hydrolysis to 3 liters. Based on your experience, what would you expect to be the challenge in upscaling to a pilot, for example, or even to an industrial scale?
So I think the main challenge is the high cost of the process. So the enzymes are very expensive, and now I'm working with a high enzymatic loading. So I think first we should optimize the process to operate with lower enzymatic loading to decrease the costs, and also thinking about the pilot scale. I think the main challenge is the high cost of the process.
High cost associated with the enzyme.
Yes, and the high enzymatic loadings.
Okay, thank you, Mariana. Licínio, we have here a special question. Do you have an idea about the specific cost per ton of processed lignin for this process? And do you expect to be lower than Valmet's LignoBoost? And how do you expect to tackle the following problem in the future? So these are two questions in one or three. Do you want to comment?
Okay. the project have different steps. Okay, this part regarding the scale up and the evaluation of the economy process will be performed later. Okay, will be performed later. This part is I think the last part of the project. Yeah? But my expectative is to, in terms of the process economy, I think the values are not very high when you compare with the lignal boost production using the traditional precipitation of linear precipitation. Okay, why? Because in a traditional linear precipitation, okay, you need some chemicals like sulfuric acid and other chemicals. In a membrane process, you don't require some chemicals. Okay. In addition, in terms of energy consumption, okay, with membrane process, I expect a very low energy consumption when you compare with the traditional process in order to get the linen by the technique precipitation. This is the traditional method. Okay. Let me know what other questions in terms of falling.
Yes, to tackle the falling problem in the future.
Okay, the idea regarding the use of the preparation of mixed matrix membrane is to minimize the falling. Okay, is to minimizing the falling.
It's already a strategy.
Let me, yeah. It's important to mention the results presented in this presentation, in this conference. They are the first results, the preliminary results. Now we have more interesting results. We got some very interesting results in terms of the falling improvement and in terms of the membrane performance. Okay, but I believe that this kind of membranes, mixed matrix membranes with zinc oxide nanoparticles, are very promising membranes. Okay, in order to get a better performance in terms of the falling. Okay, low falling tendency.
Okay, and another advantage is the mesocellulosic rich stream that you are getting from your process.
Yeah. When you compare the results in terms of selectivity, when when you compare the results with these kind of membranes with ceramic membranes, okay, our membranes promotes better selectivity in terms of the separation, the separation between lignin and hemicellulose.
Okay, thank you very much. Thank you all. So we have finished our time for discussion and questions. It was a very good session. Thank you all again, and the audience for being here for the questions. So this is last session for today in this room, but let's move to room Coimbra. For another session related with pulp production with the chairman Amadeu Santos. So thank you again and hope to see you soon.
Thank you.
See you.
Bye
Okay.
Bye.
Thank you.
Bye.
Bye bye.
bye. Bye bye.
Bye bye.